Welcome everybody to experiment 1 of EE310. I'm sorry that we're going to have to be doing this virtually, but as soon as we can, we'll get you into the lab to do these hands-on. So the experience for today is I'm going to do the lab for you, and I'm going to let you watch and take notes, and I'm going to expect you to write a lab report and hand it in as if you had been here. If you have any questions, we will be talking about this in lecture, and the lab handout is available on Canvas. It's been uploaded already. So why don't we just go ahead and get started. Before we do a couple of just basic guidelines, I like to turn the equipment on when you first get here and give it a minute to warm up. And then once it's turned on, I suggest you refrain from turning it off and on. These things like to just warm up and stay warmed up. So turn them on at the beginning of the period. Don't turn them off until you're done. So what we've got here is we've got a DC power supply. We have 2 multimeters. One we'll be using as a voltmeter to measure diode voltage. The other one we'll be using as an ammeter to measure diode current. So what I'm going to do is I'm going to take the data points point by point, and the numbers are going to be here on the display, and it'll be up to you to write them down and do the graphs and the calculations. And so also a breadboard. I don't know how many of you are familiar with breadboards. We're going to talk about those a little bit. And then here we have diodes that we're going to test. And then one other piece of equipment I'm going to show you is the curve tracer, which is this over here. This is like an oscilloscope, and what's nice about this is it gives you the entire diode IV curve in one shot instead of having to take it point by point. So you can get, here's your diode IV curve, there's forward bias and reverse bias, and you can adjust the current this way and the voltage that way to scale up to any size that you like. And so it's a good idea if you're testing a diode to put it in the curve tracer first. What you do is you turn the voltage all the way down, then it's okay to touch this. I would not touch this. This is able to go up to 1500 volts here with the cover down. So make sure you turn this down, but then you just take your diode like this and you pop it into these prongs, turn the knob, and the current shows up. It's a good idea to check your diode before you actually take data points on it. I don't want you to waste a half an hour measuring data points on a dead diode. One of the things you can think about is what would this curve trace look like if the diode was burned out? What would it look like? So if the diode was burned out in an open circuit, you would have a flat line here. It's as if the diode wasn't even plugged in. It would look like that. If the diode was shorted, what you'd have is a vertical line. So this is not only good for verifying that your diode works, but it's good for diagnosing what's wrong with it. So a nice thing to have, and so we have 4 different diodes here. This is the 1N4148 diode. This is a very conventional, it's like the Toyota Corolla of diodes, but we have 3 others. And so the things you can notice on this, for example, this has a horizontal of 1 volt per division, and let's scale that up. And we can see that now this is 0.2 per division, so this diode's turning on at about 0.3 volts over here, which means it is probably a germanium diode, or it could be a Schottky diode. Okay, and then another type of diode we have is this one here. And this one is turning on at 0.2, 0.4, 0.6, 0.8. This is coming on around 0.7 or 0.8 volts. This is a silicon diode, and we can also take a look at what's going on in the reverse direction, and you can see how it's breaking down in reverse bias here. This is a Zener diode. Okay, and then we have one other. And this also at 1 volt per division, we can turn that up horizontally. 0.2 per division, again 0.2, 0.4. This is also a germanium or Schottky diode. Notice that this has a rounded section over here and some slope to it. The rounded section over here means that it turns on gradually and not sharply like the 4148 does. And this slant here, instead of being more vertical, having it more slanted like this, means that this diode has some forward resistance to it. It is not as ideal a diode as the 4148, which is this one here, which is ironically enough the smallest of the diodes. Oops, is that the 4148? That one appears to have even more horizontal, more resistance to it. So, oh, this isn't the 4148, no. Let's see if this is it. Yes. You can see how this diode is much, that's a Zener. You can see how steep this is when in forward bias, but this one also you can see how steep this is in forward bias. And again, that indicates a diode with a low forward resistance, which is a good thing to have. So these are things to watch out for when you're trying to distinguish a good diode from a bad diode. A good diode will turn on sharply. It'll have a nice corner right there. It'll come on steeply this way. And in reverse bias, it will not slope downward. It'll hold flat in the horizontal line here. So that's a diode that's not leaking in reverse. Those are three numbers we use to describe the quality of a diode: forward resistance, reverse leakage, and abrupt cut-in. Okay. When you're handling a diode, diodes are, we're all used to seeing the symbol here of a diode with the triangle and the bar. When you're handling a diode, the package is always going to have a stripe to one side. That stripe is the cathode. It's the flat part over here. So whether it's in a glass package like this, there's a black stripe to the right side, or this, probably easier to see, or this. These are in a glass package and they have the stripe in black. If you have a diode in an epoxy package or a plastic package, you'll see a silver stripe. So the stripe to the right is like this with the cathode to the right. The terminal on the left is the anode. So when you're handling diodes, you'll know which way they go. Okay, so what we're going to do today is we have three objectives for this lab. We're going to measure the IV characteristic of this diode point by varying the voltage across the power supply, the V in here, and recording the diode voltage and the diode current. And then we're going to plot diode voltage versus diode current and hopefully get a graph like we saw on the curve tracer. Okay, that's part one. Part two, we're going to build this circuit here, which is a Thevenin source driving the diode, and try to predict the operating point of that diode from the Thevenin source. And then we're going to put this circuit together and actually measure it and see how close the prediction works. And I'll do that on the board after we talk about this. And then part three is we're going to use some data points on our curve to try to calculate values for I sub s and n. N is the emission coefficient. That's a constant that varies from 1 to 5. It's based on the composition and the structure of the diode. And then I sub s is the reverse saturation current. You all remember that nightmare-like formula we had last semester in 341 for I sub s. You will not be able to do a calculation of actual I sub s, but you can look up the spec sheet on these diodes on the 1N4148 or the 1N914 diode and look at worst case leakage current and just make sure that the I sub s that you get is less than that. So if the worst case spec might be 0.1 nanoamps and you get an I sub s of 0.002 nanoamps or 2 picoamps, then you've met spec. If you get a value of n between 1 and 2, and these typically work out pretty well, again, you'll have arrived within spec. Your lab reports will not be graded on your data. They will be graded on how you explain your data. So if you get an I sub s or an n outside that range, don't fudge it, don't worry about it, just try to tell me what you think happened. So with that, we're going to head and get started with the experiment, with the hands-on portion of the experiment.